One more type of molecule we want to talk about is amines. So amine is just any organic compound that contains at least one nitrogen atom. Okay, that's single bonded to everything else. Nitrogen atoms tend to form 3 bonds and have 1 lone pair. So methanamine is the simplest amine. You'll also note for naming purposes, you just put the word amine in there. There's nothing fancy. We use the old-timey method. But you just got a carbon atom bonded to a nitrogen atom, and nitrogen atoms tend to form 3 bonds and have a single lone pair. And you also note here, blue atoms are what nitrogen shows up as. So a lot of times amines will look like kind of the previous molecules we've seen, like alcohols, where the nitrogen part is just kind of decorating. It's kind of hanging off the side, providing some functionality. But because nitrogen atoms can also form multiple bonds, they can form multiple bonds to carbon atoms. So amines can work like ethers did, where the oxygen was kind of part of the backbone holding the molecule together. In the case of oxygen, we distinguished alcohols and ethers because they have different properties. But in the case of amines, we don't. Anywhere there's a nitrogen atom that's just kind of single bonded to things, or even double bonded things, we just call those amines. Anytime there's a nitrogen atom in a molecule, we call it an amine because these are more similar to each other. It doesn't really matter as much in terms of what properties we see from the compound. Amines usually smell really strongly and really not good. So trimethylamine is the smell of rotting fish. You'll note there's some other line angles we've drawn here that have 2 nitrogens in them. This is called putrescine. This is called cadaverine. That is because it's the smell of cadavers or of putrid flesh. The reason is kind of an evolution thing where there's a lot of nitrogen in living things. Proteins have a lot of nitrogen in them. And so when a molecule, say a protein, decomposes or breaks down, there tends to be a lot of nitrogen in there. And so things that are undergoing decomposition, you tend to produce amines. And so that's why we tend to think they smell bad. So that way we don't eat a bunch of decomposing flesh. More usefully, amines also make up a large portion of drug compounds, both pharmaceutical and recreational. They tend to feature nitrogen atoms somewhere in them. So molecules, organic molecules containing nitrogen, everything from, say, methamphetamine has the amine. Nicotine got 2 amines in there. Cocaine, albuterol, asthma drug, epinephrine, wide variety of applications, stimulants, depressants still feature nitrogen atoms in them, that's just kind of a sign. There's a lot of variety here. The nitrogen atoms just tend to show up in these types of molecules because of some of the other properties we'll see that nitrogen atoms tend to impart. And that is that they're bases. When you're talking about organic molecules, amines are the organic base. The nitrogen atom has a lone pair that allows it to form bonds with hydrogen H pluses. And so all amines are bases because that lone pair can form that. So whenever we see an organic compound that features a nitrogen atom, that molecule is a base and can do acid-base chemistry. And so we can use this to our advantage because amines will react with strong acids. And so that creates what we call an ammonium salt. So say, for example, norepinephrine, you have this nitrogen atom. It can react with HCl, and the NH2 would become NH3+. So this overall would be called an ammonium salt because basically the N has an extra hydrogen atom on it. It no longer has any lone pairs. It's just all single bonded. So that's an ammonium nitrogen. And now this is a salt. And importantly, you go from this norepinephrine has solubility rules that are not in its favor. There's a lot of carbon in that molecule, some oxygens, but not quite enough. It's kind of soluble in water, but not a lot. And you would want it to be highly soluble in terms of delivering it to, say, a human as a actual pharmaceutical. But if you turn it into a salt, you now have new solubility rules. All those carbon atoms don't matter anymore. What matters is the ions that are in there. And chlorides tend to be very soluble. So all of a sudden, this is a soluble compound, right? This is now a soluble compound. It will dissolve, becomes bioavailable, right? If you put it into a person, their body can actually access it and be useful as a drug. This is a huge part of pharmaceuticals. Increasing water solubility is really, really important because most drugs tend to contain nitrogen atoms. That means if you want to increase the solubility of your drug that you're looking at, you can react it with strong acid. Generally, we use hydrochloride, hydrogen chloride, hydrochloric acid to do that reaction, and you get a much more soluble compound. So that makes it a more useful compound. It also, one of the important things, remember amines tend to smell bad. These ammonium salts don't smell bad. So that's actually like a really useful thing. People don't want to take medicine that actively smells like rotting flesh. So, you make it much more appealing to consume. It also tends to not taste as gross as a result. And so they're more resistant to oxidation, they have longer shelf lives, all that kind of stuff. They're ionic salts, they're kind of crystalline as opposed to soft covalent compounds or molecular compounds. And so this is really common, and you'll even see a lot of times any sort of pharmaceuticals in your cabinet are going to say have hydrogen chloride in them. That just means, it doesn't mean there's actually acid in the compound, just that the acid has reacted with this molecule's diamorphine, so it reacts with that nitrogen that you'll see in there. And so this is really common across pharmaceuticals, that you treat the molecules in this way with the acid to make them more useful, to make them have longer shelf lives, to make them smell less bad or not smell bad, and that kind of stuff. So really small changes, and we can recognize because the reason we can do it is because they're amines. And you also note the name dimorphine, that ends in -ine for a reason. So let's return to erythromycin, the molecule we've looked at before. We know it's an antibiotic, and we said it needed to dissolve in water. That's why we have these oxygen atoms in there. But also, importantly, they're ether oxygens, and it's hydroxyls where there's lots of carbon atoms. So these are really non-reactive, which means it's going to not only be soluble in water, but it's going to be able to survive in your stomach. If we look at the rest of the molecule, we can see we have carbonyls. Those are also polar, so they add a little bit more to the solubility. You also can't oxidize them anymore. Those are both ketone carbonyls, so they are done reacting. And then finally, we have nitrogen in there. So this, again, a little more polar, makes this thing a bit more soluble, and it's a base. So now we know some of the properties of this molecule. We can start to predict some of the chemistry that this molecule can do. So we want to look at erythromycin kind of holistically and think, how can we look at this and figure out this thing's probably biologically relevant? Well, the first thing is that carbon is the main atom, right? You can tell there's no carbons shown in the structure, right? All those lines, the fact that you're using a line angle formula, that implies it's an organic compound, and it implies there's a bunch of carbon in there. Lots of carbon atoms tend to imply that you can probably use it in a living thing. It may kill the living thing, but it is going to be certainly active in living things. 2, there's lots of polar functional groups. So, if it's just carbon, that makes it nonpolar. That means it's probably not useful for using it in people where there's a lot of water. On top of that, all of these oxygen groups are resistant to oxidation. You have ethers, you have carbonyls, and then you have hydroxyls with lots of carbon atoms around the base, meaning that, this probably can survive in the stomach. This might be something you could just eat, right, as medicine. You could take it orally. And then when you see a nitrogen atom in a molecule, that's a really good sign that this is a drug. That's a really good sign that this thing is pharmaceutically active. And finally, we haven't really talked too much about this, but organic molecules can have really particular shapes. You'll note there are all the wedges and dashes, bonds shown in the molecule. And those are indicating particular positions of all of these different carbon atoms. When a particular shape is shown like that, that's another surefire sign that this thing is probably biologically active, because there's a lot of different possible shapes, and this particular shape is what makes it an antibiotic. It's what makes it erythromycin. Okay, no questions for participation 12.5 in this video. This is the last one. There's one more left. There's one more video left. I'll see you in that video. Bye-bye.